Hi everyone, this is the topic of my talk, formation of disk galaxies. And in this talk, I will be introducing a very simple toy model and try to understand the formation of galaxies are still star forming and look like a disk. So in order to proceed, I think I would like to spend one slide just to remind you how we model galaxy formation, in particular for disk galaxies, what the basic assumptions are, and what the basic approach we normally take. So we all believe galaxies form in dark matter halos, and we assume baryons collapse into dark matter halo, simply follow dark matter, and gas can cool radiatively, or it just directly come into the central object to form central galaxy. And if the baryonic matter has a certain angular momentum, it could be supported in the central region and form a disk. And if the cold gas is dense enough, it may fragment and form stars. But when you do this, you immediately realize actually you cool too much material, and you predict too massive galaxies. So then what people normally do is feedback, because this is so intuitive. Because you have star formation and the stellar evolution may give you energy, momentum, all this output, and you can affect the cold gas when the galaxies are forming. And you can get rid of some of the actual baryon and try to fit galaxy formation into the picture. So here, this is like this cartoon show when you have gas cooling from the hot atmosphere, you form a cold gas disk, and when star form, you eject some of the material. But there are a lot of observational constraints. So when you cook up a model, you have to manage somehow to make your model fit into those observational constraints. So I think the data are accumulated to the degree we have a robust constraint. One of the important aspects is we all realize the stellar mass fraction actually is a strong function of halo mass. When you go to lower and lower halo masses, the stellar mass fraction decreases rapidly. And this is apparently, this is pretty robust result without depending on detail of the models. Different authors have very different results. And more interestingly, people find similar behavior for cold gas. On the right-hand side, what I show is a very similar technique using abundance matching for alpha-alpha H1 galaxies. So people find that the cold gas fraction for low mass halos actually is also rapidly decreasing with decreasing halo mass. So that basically suggests when you have star formation, not only you need to hide some of the baryon. You couldn't hide the baryon because the baryon is neither in stellar phase nor in cold gas phase. So it has to be somewhere else. So then when you tune the parameter for the feedback, you have to be careful to match both of the data constraints. And when you make such a model, you will realize actually it's pretty difficult to do this because cooling efficiency in low mass halos is normally high. Even you make a very strong circular velocity or halo mass dependence for the mass loading factor of the feedback, you still find you can easily overpredict cold baryon mass fraction or stellar mass fraction. So here I show a particular model where I actually carefully tuned the model in the way the mass loading factor of the feedback scales with circular velocity in a certain way. I can match Milky Way sized halos for the stellar mass fraction and the cold gas mass fraction. But as long as you go to lower mass halos, the model still overpredicts both the stellar mass fraction and the cold gas mass fraction. But here the model is actually already pretty extreme. The mass loading factor is needed to be 20, which seems not suggested by models, and also not seen in observational. And we can take another angle to look at the same problem, the number density of low-mass galaxy. This is a result presented in this paper. This is a number density of galaxies in this particular stellar mass range. And you find for those low-mass galaxies, the number density is decreasing with increasing redshift quite rapidly. And these are some particular semi-analytical models which are pretty successful in many aspects. But those models are still generally over-predicting the number density of dwarf galaxies at high redshift. And this is, confirmed by our more flexible model, which encompasses many other models. And we constrain this at redshift 0 and to look at the general trend of this exact prediction. And you find basically, as long as you make an assumption, all the baryon come into halo, simply following dark matter, and you rely on strong feedback to get rid of actual baryon, you always make this type of a general prediction. And this problem is pretty obvious. And there is another outstanding problem in galaxy formation in CDM context. You make a prediction of the cooling gas, and because you know the angular momentum distribution of the cooling gas, and you can predict where the cooling material end up with in the central disk. Then you measure the characteristic size of the galaxy. Then you compare your model prediction, which are the black dots, with these different lines, which is a decade of observational programs for the half-mass radius of stellar disk as function of stellar mass. Although there are certain variations in different observations, but the general trend is there, and it seems pretty robust for Milky Way-sized galaxies. The size of the disk is pretty large, but such a model predicts relatively low characteristic size for those type of galaxies. Why is that? Simply because angular momentum. This is a nice paper pointed out the exact problem. So here this is Milky Way size, and this is a specific angular momentum of the disk of Milky Way. And it sits right on the top of dark matter specific angular momentum. If you take a model and you allow gas to cool out of the halo, and maybe angular momentum could be lost, and also the pooling material is from the inner region, you end up with under-predicting the specific angular momentum of the disk material. So that's the reason you under-predicted the size of disk. And this is well understood physics because the solid line shows you the dark matter mass distribution from inner region to the outer region. And the red line shows you the angular momentum accumulative distribution of specific angular momentum. Simply, CDM model predicts angular momentum distribution in dark matter halos is fairly extended. So a lot of high angular momentum material is actually at a larger radii. But when you make a radius to cooling, because the central density of the gas is always high, you always predict the inside-out cooling kind of scenario. Then the inner region actually only contains very low angular momentum. That's why you always under-predict the size of the disk. So then here I would like to take another approach. Just to forget about a very strong outflow. We think about another very different model. So here I would like to propose a so-called preventive model. In this model, we don't have very strong outflow. We don't have very strong feedback. But we rely on something else which gives you very robust theoretical prediction and a very clean picture which you can understand even without doing any simulation. And here I describe this model. So first of all, I assume the intergalactic medium is generally preheated to some certain entropy. And this entropy actually could be as low as 15 keV centimeter squared, and which coincide with zero entropy of Milky Way size halos at redshift 0. And it decreases with redshift, basically following this relation. And this relation basically suggests the temperature of the intergalactic medium is a constant over a certain cosmic time. And this is showing you the entropy history in the magenta line as function of redshift. And these two black lines shows you the zero entropy, so-called. Basically is a proxy of a gravitational bond of 10 to 12 solar mass halos in solid line and 10 to 11 solar mass halos in dashed line. And here I show the zero temperature of these two different type of halos, and also what temperature implied by this entropy history. And because I assume entropy is the key quantity, and it follows this way, and because the definition of entropy follows the temperature over density to 2/3 power, when you are talking about the different over density, they may have a different temperature. And here I'm talking about. No, that's exactly the point. No, because I need the entropy to be as high as this. This is at zero density. This is 200 times of the density of the universe.
What's the temperature required?
If this is average density of the universe, then this temperature is as low as a few times 10 to the 4 Kelvin. Yeah. And when I assume this, I can solve hydrostatic equilibrium for radiative cooling, and I follow angular momentum distribution. I predict the size of the galaxy. And I have a star formation recipe following a Crumholtz model, and with very small outflow. And because the entropy has a very clean picture here, this is showing a simulation I did a few years back. And when you have an entropy larger than the zero entropy of the system, the fraction of baryon can collapse into a halo is a very strong function. It's decreasing rapidly. And it can be understood in this way. If you have entropy, because entropy defined this way, the temperature, actually, zero temperature proportional to circular velocity squared, and which gives you the baryon mass collapsing into a halo, simply proportional to zero mass of the halo to the second power. And we solve hydrostatic equilibrium by assuming entropy profile, and there is a nice analytical solution for NFW halo. And here I show the density distribution of the solutions by assuming different power index of the entropy profile. And this is an isentropic profile where entropy is a constant. And this is isothermal profile where temperature is a constant. And what you find is the density distribution of the isentropic profile is fairly extended. And you can understand then the cooling material actually from this isentropic profile is mainly from outer region, and it brings in more specific entropy than any other models. So we took mass accretion history of dark matter halos with end up with 10 to 11 solar masses and 10 to 12 solar masses, and I also fit those histories by smooth curve, and I will be focusing on those two different mass regimes, but also sample a large range of mass accretion histories to show the results. And here I show the predicted cold baryon mass fraction as function of halo mass at redshift 0, and it matches with observation quite well, which is the pink line. The other side is stellar mass fraction as halo mass, and it also fits nicely. And this is a star formation rate history as star formation rate of 10 to 11 solar mass halos. and star formation rate history for 10 to 12 solar mass halos. And the smooth mass accretion history with this entropy model gives you very nice fitting for both cases. And you can understand the growth of the disk in these two different scenarios. They are very, very different because the isothermal profile is more concentrated, and a lot of cooling material is from the inner region. It brings in less angular momentum, so the disk is less extended. While in the isentropic case, you can predict fairly extended disk, even at fairly high redshifts. And this is the prediction for half-mass disk radius as a function of stellar mass at redshift 0, 1, and 2. If you have already forgotten my fiducial prediction, I can flash back and forth. So you see the impact for Milky Way-sized galaxies is fairly large. I think this is what I want to share with you for this simple model, and this is the summary of my talk. So first of all, we have a physically motivated model, which is fairly simple and can be understood easily. And the basic property of this model is it doesn't require strong feedback, but can still nicely reproduce the baryon mass fraction, cold baryon mass fraction, and the stellar mass fraction, and also the size of the disk as function of stellar mass at multiple redshifts. That's it.
Questions? Reinhard.
Seems to me that any kind of a model which tries to solve this problem with preventive action from gas not getting in at whatever redshift will naturally, and I think you've shown this, lead to two things. Confirmation rates of high redshift, and also low surface density in gas. The third, although you've not shown that, I think it would be implied, low middle distance. So it seems to me that is something one would have to compare to observations. But one case should show, it seemed to imply, redshift 2 for a typical 11 solar mass, halo, what, 0.1 solar mass per year? Is that right?
No, the star formation rate is always low. This is 10 to 11, and this is 10 to 12.
That's the halo mass.
That's the halo mass.
I understand that, but so what at redshift 2 is the predicted star formation rate?
Here, the red line.
Yeah.
The cyan band is from Barozzi result. This is empirical.
Sorry, but is that not 0.1?
0.1, lower than 0.1, I think. Yeah.
The halos, that the mass at that redshift 2 actually is lower, right? That's
Right. This is the progenitor halos. This is progenitor halos.
Observations show us that the main sequence for 10 to 11 solar masses at redshift 2 is.
No. This is 10 to 11 at redshift 0. I'm showing the progenitors. This is the history of particular halos at redshift 0.
Okay. That's very hard for me in my head to transform that.
Yeah, I can, if you have.
To put it this way, on the right panel, that's the Milky Way. And then at redshift 2, it's about 2, it's about 10, so higher than the Milky Way mass, it'd be higher.
Okay, but that still is low. That's my point. Absolutely. I think you will find in the main sequence of the 11 solar mass object.
But it's not 10 to 11 at redshift 2. At redshift 2, the Milky Way is 10 to 10.
Yeah.
Yeah, it's 10 to 10. Joel.
In the kinds of simulations that seem to produce realistic-looking disk galaxies, there are several processes that are very different from this temperature floor or entropy floor that you're putting in. One is that there's starbursts and AGN phenomena in the center that eject a lot of gas. And so that would get rid of a lot of the low angular momentum material. And then there's the cold flows that bring in high angular momentum material from considerably farther out. Do you think that if you included those features instead of the entropy floor, you might get realistic histories of star formation and gas?
Okay, I think I have tried very hard based on my previous version of the models. But my experience tell me actually it's not that easy, although all these arguments sounds very, very plausible. What I'm saying here is that this model has to be true, but just illustrates this physically motivated model gives a very clean picture, and you can test this model from all these features I presented. So there is a very clear observational implication out of the model can be tested.
Yeah, but I think one of the problems, one of the things that Reiner is worried about, I think, although he focused on the total star formation rate, which looks okay, but if you have this entropy floor, I suspect you're going to not have the instability that gives rise to the clumps, and we really do see the clumps.
Yeah, actually the disk instability part is missing from the model, but I would really like to evaluate that part.
But the fact that the gas actually is 1 is okay.
The gas fraction.
Yeah, the gas fraction. You are saying the gas distribution is not okay, basically, right?
But
Otherwise,
because of the size of the galaxy also fits the data.
okay. Right.
So unless the galaxy disk is still exponential, it should be fine.
Well, the point is that if you increase the entropy, it must lead to an increase in Q, and therefore.
I'm not sure because this entropy is a hot gas, right? It's quite a different physics.